So our technology folks are letting me start to talk here. Everybody hear me okay? Good? Life good? See the screen all right? Good. My name is Bruce Matthews. And the logo that's up there is the company I happen to work for today. I'm not trying to sell you anything with this presentation. What I'm trying to do is provide you with a lot of information about a fairly new topic in technology, and to give you some outline of the architectures, the textures of the architectures that are available for what we call service meshes. And since this is sort of a new technology, I've been messing around with it at home, and I've got a 4-year-old grandchild. And when I first made the initial one, I used a version called Istio, and I told my grandson, Ashton, go tell Mimi, go tell my wife that I made a shmesh. And he said, what's a shmesh? Well, it's a service mesh. And he went out of the room, and a little while later, my wife came back in with a dustpan and a broom. Like, where's the shmesh? Anyway. So today's topic really focuses around service meshes. I just wanted to let you know I've been doing this a while. So there's 40 years worth of technology sitting up there, going all the way back into the 70s before the internet existed. I think it was before Dirt existed, but that's okay. How many people have ever worked with a service mesh? Okay, great. We got a few people who have played around with it. And have you deployed more than one? Okay, cool, great. So what I'm going to be doing is giving you an outlay of all of the different service mesh architectures, how they apply to each type that's out there in the market currently, and then give you some thoughts on which ones work the best in which use case scenarios. So let's start off with the fundamentals first. The service mesh itself provides a set of secured communication between microservice services in a cluster. Now, we're talking about Kubernetes here, but it isn't limited to just Kubernetes. You know, there's a thing called KubeVirt inside of Kubernetes that runs a virtual machine inside of a wrapper. My company provides one called Virtlet, does the same thing inside of a pod. So this service mesh actually can introduce that secured communication between not only the microservices, but virtualized services as well. They are made without having to change a line of code. So your developer environment is really happy about that. They get injected with all of the things they need from the service mesh to support all of the features and capabilities of a service mesh that I'll be getting into in a little bit. So, the primary reason for using a service mesh is to satisfy those needs. And the initial one, service discovery, is saying, hey, what services do I have access to? Do I have load balancing? Do I have secured TLS? Do I have circuit breaker patterning and stuff like that? And I'll be getting into those in more detail in a minute. But that's the primary ability to discover that. And many of them use open source tools like Core DNS or something of that nature to help provide that capability. And then there's the load balancing aspect of it. This is the most fundamental high availability portion of a service mesh. You really need to be able to switch from one to the other, and to know how the traffic is going through each one of those channels to be able to decide whether to add more or reduce them down to improve the performance of the overall hardware you're dealing with. Then, of course, there's this idea of security. And anybody who's been dealing in Kubernetes for a little while, it wasn't something they thought of initially, But the reality is you have to build in things like encryption and secure transmission and all of that. So a service mesh addresses that need. Authentication and authorization, certificate generation, so that I know that this transmission from service A to service B has a certificate that will allow for this particular transmission and transpire or expire on the next set of them and get renewed habitually to allow me to be a traffic cop for the traffic that's going on underlying it in the network. And then, of course, this circuit breaker pattern issue. Developers hate to think about things breaking, but they do. And when they do, the reaction, the place it's supposed to go when that one doesn't work, needs to be defined. Well, a service mesh can literally say, reroute the traffic. I know the load balancer going to here has ceased to provide service back. I can measure that. And as a result, I am going to cut that out of the equation. What will that do? That will stop a lot of traffic going there to 404, going there to 503. Instead, it will come to a live channel instead that got automatically scaled as a result of the first one breaking. Okay, so those are a few fundamentals of what a service mesh is and some of the basic features that all of the service meshes that I'm going to show you have built into them. Some of them to a better extent than others, but let's go from there. So the key benefits are the ability to shape the traffic going from one service to the next service in a cluster. And those services might not be in the same cluster. They may be regionally disparate. They may be actually not at the other end of it a Kubernetes cluster. It might in fact be an OpenStack virtual machine. The fact that it's able to connect via TCP/IP and take advantage of TLS protocols to connect can all be handled by the same service meshing. And when you do that, you can actually shape how much traffic is going through that. 80% goes to service A, 20% goes to service B. I can switch those when needed. I can reroute and say another node will pick up the additional 80 and split it into 40 and 40. It's because I know that the machines can't handle it all at once. Quality of service is also a major issue that from networking folks, nobody has down, and we're just starting to develop all of the metrics that you need to apply to maintaining quality of service in your mesh. As a result, we keep capturing a lot of the capabilities, the actual throughputs and volume of data going through each one of these paths. And then we're able to say, well, skinny this one down and increase the bandwidth of this one in order to make sure that the people at the other end are getting the best possible service out of the overall application. Those are the kind of things that service meshes now inherently provide. And of course, as I indicated before, that idea of being able to break the circuit to prevent cascading failures from inhibiting the throughput of your application within the containerized world. So those are all very neat capabilities, but the most neat capability is that it's done without the developer having to know how it's done. Like they don't have to build it into their application, and we'll be getting into that in a minute. So when these service mesh architectures started to be developed, they didn't have a good idea for how it was going to be done. So the initial structure of the architecture was done like we had been writing C code for a long time with shared libraries. The shared library versions were kind of thick. They might involve things like JVM and other languages that would get actually posted into a container. So the container would not only have the application code, but the library code that was able to run all of the service mesh functions. That library would then talk to a control plane from the data plane, and that was how it knew there was a load balancer or knew that it had to circuit break or any of those kind of things. Then they said, well, you know, that's pretty thick, and every time I make a change or I add something new in the library, I got to go run around to all of my containers and re-inject them and redistribute them from the repositories so that they know what's going on. They decided that it would be better to have a centralized source on each node. So they came up with this node agent concept. All of the traffic from one container talks to the node agent. The node agent actually is responsible for transmitting the data from that node to the next node or the control plane, keeping everything in sync. It thinned out the code that was required to accomplish it and made it easier to deploy and all of those things. But I think you probably know what the problem would be with that architecture. If it fails, if it stops doing the agent work on that node, you lose all the containers. There's no more traffic going through it. So they said, aha, we've come up with a better idea. So they invented this whole new capability called sidecarring. So every time I create a container in a cluster in a particular namespace or out in the default namespace area, it will actually create a secondary container. That container's job, that whole reason for being, is to intercept all of the traffic that's going from that container somewhere else. So even if I've started generating that container's traffic at a non-TLS oriented way, it becomes TLS and secured oriented in the proxy service that's sitting inside of the sidecar and gets then transmitted up to where it's supposed to go in a secured way. The same thing happens at the other end, except it de-encrypts and comes back down to the container on the other side. Same thing going forward and reverse. And these multiple threads keep track of all of that kind of traffic for it. So those are the three basic types. You had the library type that started it, the node agent type that was the second iteration, and finally we went to this sidecar methodology, bless you. And so those are all of the SMEsh arcs that are out there at the moment. So here's a little, more information about the library version itself and how it worked. The microservice had to have all of that additional ancillary code built into it. It was sort of an adopted practice by old guys like me who had written code in C and all of those kind of things. Made a lot of sense to us at the time, except it was really, really hard to maintain, and you had to manage the versioning of everything so that all of the tools would be available to each of the containers and needed to be updated, and you had to remember to do that manually or outside of the service mesh itself. And some of the early adopters of it, Twitter, Finagle was the first one, I think, that came out there using the library approach. And of course, Netflix came up with their own, and they developed a couple of them because they didn't like the first version of it. And what happened, they had to pull out the code from all of their containers and put the new code in for the ribbon version of the library, and it got to be really messy. Okay, so the node agent. Folks from Buoyant started a project called Linkerd, and Linkerd had that individual node agent. It was written in Java. It was very, very heavyweight. And as a result of it, all of the aspects of the transmission of data going from two places was kind of constrictive and slow. But hey, Linkerd invented this node agent thing, and they carried it forward. And a couple of other companies, Consul was another one, who picked it up and said, yeah, let's try and see if we can improve on this topic. And we'll get into how Linkerd evolved more in a little bit. But the big advantages to it was that you could distribute one copy to each node. You didn't have to carry it with each one of your containers, so it was easier to update it and all of those kind of things. The bad news is if it breaks, you lose all the container traffic on that node. So this final version, the Sidecar version, this is, of course, the Istio came into play here. That was the one that I had the first exposure with to dealing with the Sidecar version of the thing. And really, there were a whole lot of benefits. As you can see, I couldn't find very many downsides to this because I can inject all of the service mesh capabilities, that circuit breaker, that load balancing, that all of the things that need to happen as a standard from my operations side into a container that doesn't know anything about how any of those work. It just knows that I've got a partner, which is a typically Envoy proxy, that gets intercepts the traffic and distributes it to the load balancer, makes sure it can be circuit breakered, all of those kind of things. So this is now the predominant way people are creating the new service meshes that are out there in the world. Okay, so now we come to some comparative data about service meshes themselves, which ones are out there. So smesh comps. I broke them down in two categories for you because obviously there are some people who do a licensed version of a service mesh that you can include, and they do a subscription model, and it's typically per node that's connected to it and all of those kinds of things. So I've broken those down on the right, or on the left, your right, and then the totally open source offerings, where the plus is I can get it from GitHub and deploy it, and they typically have READMEs that tell you how to do all of those things. The downside is that there's nobody to phone if something doesn't work the way you think it should. You can talk to the open source folks to start contributing yourselves, just like we've done in the OpenStack community for the last, since 2010, right? Okay, so I think starting with Envoy, Envoy just started out as a proxy and then started injecting or glomming on all of these additional services as they came about being created and configured into the idea of a service mesh. Istio actually had sort of had an advanced thinking on this subject, and they had started with the whole framework involved and made it pluggable and modular. So although they use Envoy currently as their proxy, they could unplug it and use Nginx, or they unplug it and use whatever features or capabilities you particularly want to use to support that need. And then, of course, there are others like Aspen Mesh who actually use Istio as the foundation, and they built their own construct for the control plane layer on top of it. Okay, so let's go through the open source service meshes that I had in that list, and we'll give you some detailed information about each. So let's talk about Envoy, the sidecar methodology. And it was originally like in a project done by Lyft about 2 years ago, 2.5 years ago. It provides the two key elements, one of which is the proxy services themselves, and the other of which is the circuit breaker capabilities that then get embedded into Istio when it's used as the proxy service. It's really fast. And the reason it's really fast is they broke down the threading model into 3 categories. The first one is they have one main thread or multiple main threads that actually monitor all of the other threads and make sure that the transmission of data from one place to another is being handled properly. And then worker threads that actually do the heavy lifting, the I/O, going back and forth between containers. And finally, when you don't need a thread anymore, or the memory that it's allocating, they have a file flusher that intercedes, just like the garbage collect, for example, on Java or something of that nature. That design lowers the amount of demand on the physical servers that you're dealing with, and provides really fast performance, and I'll give you some numbers on that in a minute. Istio, the second one in the list, they added this whole idea of the control plane. So now we separated out control and data. So, and the whole idea of this is to be able to give visibility external. So there's a tapping mechanism inside of the, they call it mixer, inside of the control plane portion of Istio, and that's actually to allow you to do observability using things like Grafana and Prometheus underlying to capture the data. That then leads you to being able to apply some AI learning capabilities like, gee, if I get to 80% here, what do I do? Here's the policy that's established to handle that scenario, and that's all built into the control plane capabilities of the Istio itself. Then Envoy can just do the job of proxying, which is the thing it does fastest. So that's kind of where Istio lives. So the first iteration of Linkerd was the one that I said, written in Java, and it only did a certain amount of throughput, and very heavyweight, so it took up a lot of space, required a lot of CPU and RAM and all of those things. And if it failed on one node, you lost all of the node traffic from all of the containers sitting on that node. But it was their first iteration of it. And I was really fortunate. The guys from Linkerd actually called me because they knew I was going to be presenting this. And they said, no, let me give you some additional information about Linker and Linker 2. Linker 1, that's this one. Linker 2, and here's the differences between them. So it gives you a better look at what Linkerd 2 version 2 can do at this point. So now it's really, truly a service mesh. It was rewritten from Java into Rust and Go. So Go for the control plane aspects and Rust for the proxying data plane services. Thinned it out. It has about 50% less CPU than Linker 1 required, and uses far less RAM and stuff like that. So it's easier on your piece of hardware. Okay. So those were all of the open source service meshes currently out there that are competing for space with this new technology. And out of those, you know, Envoy is looking like, or Istio is probably looking like the one that's most prominent in the marketplace right now, but it's not the only one, which is why I wanted to show you all the other ones. So let's take a look at some of the commercial offerings and see how they differentiate themselves. So Consul, they were back in that node agent world, and they've not changed that yet. They were originally developed by HashiCorp. So HashiCorp came up with it, and if you have a problem with Consul, they are the folks you can call to actually help you figure out what's wrong and figure out how to fix it. But it's on a subscription basis, you know, per node within the service meshing capability. Aspen Mesh took advantage of Istio, basically, underlying. So you'll notice that the underlying data and control planes look very mysteriously like Istio. But then they've written a whole API layer on top of it that allows you to be able to connect up to your corporate enterprise service tracking systems like Splunk or Splunk and all of that kind of stuff, so that you can start gathering the data and pushing it off to your service teams to be able to manage this thing. They've had their own UI that they developed, and here again, a lot of this stuff now is written in Go. It's the latest and greatest language. If you haven't looked at Go, highly recommend it because it's going to be common throughout the Kubernetes architecture, cloud native architecture. So this one I found was kind of interesting. Kong actually can work with any type of cluster. It doesn't matter whether you're talking to an OpenStack environment or a Kubernetes environment or any kind of KVM-oriented framework or anything else. But here again, it's a commercial product, and they have their own licensed versions of logging and authentication and caching. They are not open source versions. And if something breaks or doesn't work the way you think it should, you can call them and they will come and fix it. And I had some great conversations with these guys actually about their service levels. And they're highly knowledgeable about service mesh technologies and how to establish them for an enterprise-wide deployment and all of those things. But they're on the pricey side. That was the only thing I can tell you. Okay, and then I thought I would sort of throw this in as the side note, okay? Because oddly, AWS, right? They do almost everything, and it's my own variety. Route 53 for DNS and all of those things. They control everything. But this one, they said, well, Istio and Envoy are actually working pretty well. We might as well just go ahead and use them. So everything that's deployed is really Istio with Envoy, and then they use Grafana and their own database service as the control plane side of it. But it's a really minimal implementation. It doesn't do all of the circuit breaker stuff. It doesn't do all of the load balancing that you'd like using alternatives. It will only use the AWS load balancer in their world. So they've cut it off at the knees kind of to accomplish what they were doing with it. Okay. So now that you've got this overview of all of these 8 service meshes, the commercial type and the open source type, let's take a look in more detail at each one of them and the neat features that they have in them. Almost all of them start with gRPC support and HTTP because those are the 2 most prevalent means of trafficking between containers, REST and HTTP. They all have an API-driven kind of interface to them. Most of them have a binary, like there's an Istio CTL, Linkerd CTL. It's that kind of a thing, that you can do everything from the API at the command line. Good for scripting if you're not somebody who does REST calls and all of that kind of stuff. Istio has, of course, that ability to do fault injection. Why is that important? If your application can break in certain ways, you want to test them before they actually happen. So you can inject a fault and say, what happens if this happens? And let me figure out the route that it needs to take if that one breaks. And of course, gRPC, the policies and procedures to be able to say, encrypt the traffic in 256 WIT diffie from here to here, and then translate it into standard 64-bit encryption so that it can be received on the other end. All of that can be done with policies inside of Istio. And you can use it on multiple types of platforms. So you're not necessarily stuck to the GKE or on-prem version of Kubernetes or AKS or any of those things. It will work on all of them. And you can do hybrid deployment with it. Literally, I can have a cluster sitting in GKE, and I can have a cluster sitting on-prem, and I can use the same service mesh across both of them, which is really cool. It's neat to watch when you can do it. It built in disaster recovery and all that kind of stuff. Kind of nice thing. Okay. So this was the thing with Linkerd. When I originally talked to the guys, or before I originally talked to the guys, it looked as though they were the same features and capabilities between Linkerd 1.0 and Linkerd 2.0. And in fact, once I talked to them, he said, well, Linkerd 2.0 is a little bit behind because we rewrote it and go in Rust, and we didn't quite get all of the capabilities with all of the feature richness that we got in the Java version of it and all of that. But Linkerd 2 is just way faster. it's faster than Envoy, which is kind of a weird thing, you know, that they slimmed it down. They took all of the stuff out of it that didn't have to be in a service proxy and just left the proxying. So whereas Istio and others are sort of like a Swiss Army knife, this is more like a needle, you know, just injecting that at the right point in time and having no other capabilities built in. But an interesting concept. And both of them are fully open source. If you need service on something, Buoyant provides it. They're the guys who funded the project originally. Okay, so I got into some real interesting discussions with these guys, and he wanted to make sure that I told you guys everything that I knew about the two different linkers and the positives and the negatives. So we built an actual table that told you, you know, here's all of the capabilities, the, you know, less than, you know, a 10 megabyte footprint versus 100 to 150. Apache licensing, they've in Go and Rust instead of Finagle and Netty and Scala. And all of the supported platforms. For right now, Linkerd 2 only works with Kubernetes deployment, but it will work with all Kubernetes deployments, whether they're on-prem or in a cloud of any kind. I think that was were the most important points. The load balancing, like I said, they've got some statistics here in a minute I'm going to give you that sort of tell you what the best things about the Linkerd D2 version are. All right, so the last couple of these, Consul, you know, single binary approach, easy to manage and maintain, can deploy at scale, all those things, and the Consul folks from HashiCorp to call as the throat to choke. Whereas, and Aspen Mesh, they're a separate organization. It's Istio. So if you know Istio, that's what you're getting. You're really getting then the service from them as a, I'll support it and sustain it. And you don't have to know how service meshes work. I don't know. I'm more inquisitive than that. I like playing around with Istio and figuring it out for myself, but that's just me. Kong, and here, you know, they put in a ton of engineering effort. So I can understand why they charge you the subscription fees for it, because you know, they've done eloquent software development with it. It's all proprietary. It's not, there's nothing in it that came from the open source community at all, but now they have an open source front end to the thing, and they'll let you do the API gateways using open source calls. But underlying it, I have no idea. It's a black box. However it works is how it works. They use their own load balancer. They use their own mechanisms for circuit breaker. All of that stuff is proprietary to them. And AWS, of course, hey, we want to get in the Kubernetes game. Let's use something and throw it out there in the market and see who it sticks to. Anyway, that's kind of how AWS is. Okay, visualization. This is a really, really important part of what service meshes provide to you. It's not just the capabilities, not just the circuit breakers, not just the load balancing, everything else. It's being able to visually see what the heck is going on inside of your cluster and how to improve the performance of one thing over another. So, okay, most of them out there in the marketplace, they all look mysteriously the same. They use things like Prometheus as the underlying trending analysis storage. And of course, they provide Grafana at the top end, so it displays templates. You can customize the templates. You can add your own things to it. You can integrate those with your own Grafana stuff for other application services. But that's pretty much, and almost all of them, the 8 that I showed you, have something like this. Either they wrote themselves, like Linkerd did, or Aspen Mesh did, or it's something it's just Grafana and you can create your own templates and do all of the things you want to do with it. Okay, performance. Perf Shmesh. That's where we're going now, and we're almost done, so I hope you can hang in there with me for this last little bit. Okay, so when you're trying to figure out how to gauge these things for yourself, it breaks down into a couple of categories and that affect the performance of how your service mesh is going to work in your environment. Let's start with just the control plane, and if you have a tremendous amount of ongoing deployments, it's going to start slowing things down in your service mesh, which means that you have to monitor and keep track of what's going on so that you can make changes, introduce changes in the pipe, the bandwidth of the pipe, and all of those things based on what you see in the visualization tools that they provide. If you change your configuration, I'm going to add persistent storage. I'm going to put in Nginx as my load balancer instead of the one that I got originally. And I'm introducing all of those configuration changes into the environment. It's going to slow down the service mesh until you go back through, look at the visualization, make the changes to the mesh itself to accommodate it. And finally, that idea of the number of proxy connections. So how many containers are you going to support? How many sidecars are you going to have as a result of it? That kind of thing. From a data plane standpoint, pretty simple. How many clients on each node? How many targets get requests out of those? So there's a lot of inter-process communication between clients on the same node or clients on different worker nodes. That's going to add stuff. How many cores am I supporting and throwing at my containers themselves, and the number of bytes that it has to read through to know how to filter this particular throughput. So that's one of those policy things, right? So if my policies get really sophisticated and I say every 5th bit, transfer it over here and take these 2 other things and redirect them there, if this happens, it's going to slow down your service meshing. Fortunately, there are some tools you can use to take a look at that before you actually implement those kinds of changes. The 2 that I found that were helpful were fortio.org and BluePerf. So those 2, you just download them. They're open source, and you can, they have scripting and stuff like that, templates to help you figure out how to run them against your service mesh. Once you do that, you can gather the data from that and figure out how to change it to make it faster, better. Faster, better, cheaper, right? Those are the 3 things. Okay. Now we actually get into some of the load balancing aspects of this. And the reason I chose load balancing is for everything else that it does, traffic shaping and everything else, it boils down to how fast the load balancing actually works inside of a service mesh. I picked these, Nginx, HA Proxy, Envoy, Trafic for the European community, and Amazon Application Load Balancer just because I threw in the AWS stuff about the other thing. Voila. I told you Envoy was fast. That is actual data of requests per second using exactly the same FortIO templates against each one of them and running it through. And you can see that it's handling 2,500 to 2,250 of requests per second. And you can go to that website to do that comparison. The next best one actually was HA Proxy, I think, out of all of the open source ones. I really don't count ALB as anything but their version of it. And then the second thing that affects it is latency, right? So it's not just the number of requests that I can handle, but it's the actual latency built into the time. And as you can see, they're all pretty good until they start to get up into the 90th percentile. And at the 99th percentile of throughput demand, a lot of them go absolutely bonkers. The least bonkers is Envoy and HA Proxy. And so as a result, if you take those 2 numbers and do the math against it, both of those, HA Proxy or Envoy, are pretty safe bets in terms of using as your load balancer. And you can go once again to that site to go look at the data. However, and this is the gentleman from Linkerd and Buoyant, wanted me to make sure I told you that there's some disagreement about the numbers and the latency, and they've done their own testing. And this is that Linkerd 2 set of tests for themselves that they ran. I didn't run these. I ran the other ones, right? So I know that those were the numbers. They dinked with how the configuration was deployed of their own Linkerd product, and they put the proxies in a different place, and they moved the control plane around and all of those kind of things. And they got it to be pretty, you know, perform better overall with less latency and you know, higher bandwidth. But you'd have to talk to them to find out how they did it, because I don't really know. But they wanted me to point that out to you. They were like adamant about it. Okay, so now we're going to go really quickly through the pros and cons. Those 3 different architectures that we started with, I mean, the pros, and we've sort of talked about all of these, so I'll summarize really quickly. That there's a strong coupling with the application service layer for libraries. It's hard to manage and maintain them, but they are, you know, it's self-service adoption. The developer can stick the library in his container code, and voila, he's off and running. Node agent, it centralizes the thing on the nodes so that, you know, I only have one to deal with on each node, and that all the traffic goes through it. So that's the advantage. So I can monitor it from that agent. The bad news is if it breaks, I lose all of the traffic from all of the containers that are underlying it on that node. And the sidecar, the biggest advantage is really granular. It's very small, very slight, so you don't have much overhead on each one of the containers, and that it allows you to do all of these service mesh capabilities, features, like load balancing, circuit breaking, all of that stuff in a centralized way, so that the operations team can feel, you know, like they've got control of something, and that the developer doesn't get interfered with too badly. But the disadvantages is that there isn't a centralized way of enforcing it, making people use it. The developer has to decide to inject it, otherwise it doesn't happen. So that's that one, and we're almost at 5 o'clock, so I'm gonna hurry. Some final thoughts. So I think Istio right now, which presented to the Cloud Native Foundation last year, actually, is probably going to be a project member in the same state as Linkerd and the other guys that, you know, make that a big deal. What that really means is there's going to be a whole lot more developers working against it. So it's not just the guys at, you know, Netflix that used to work on it, or us, but it's going to be a lot more people. Everything's fully open source in the Istio framework and everything, so we can unplug and plug new stuff in as it comes along and gets better. That there will, the things that are important now is what use cases themselves can be applied to this. And then, you know, from a bottom line perspective, everybody's going to have a service mesh, guys. It's every Kubernetes cluster out there is going to use some form of service meshing. It fills a hole that's not currently filled in the Kubernetes orchestration framework. So I guess we all ought to get used to it and try and figure out, you know, how to make it work best for each of us. If you are considering using one, we write blogs. That's a good way of doing it. I've got one called the Shmesh Returns that keeps coming back. You know, it's like a bad penny. But it's that kind of thing. So you need to keep track of it, because this is changing like really, really rapidly. It's a very fast-moving part of our technology life. So you need to stay up with it. And if you haven't decided yet to take a look at it, you're behind, because there's a whole bunch of other people who have already started looking at it. And so I think that's it. That was all I had from an information standpoint. I hope that was helpful to have that information. I'm going to put this stuff up on the OpenStack site when they ask for it. So you'll have that. The video, the guys back there are doing that now. Has anybody got any questions?
maybe you know some service mesh for different protocols than TCP?
Yeah, so there's a few of them out there that are starting to look at doing UDP traffic as well, which is, I think, the whole.
Yeah.
But we haven't found one yet that actually has adopted it.
I've got one. Network Service Mesh, NSM.
Oh, NSM.
I didn't want to hijack your session. It complements Istio. So I love what you did for Istio. It's great work, man.
Thank you.
NSM, we're looking for coders.
Good for you. Let's make sure that we connect up so I get that information. Thank you. I'll add it to this presentation. Okay, perfect. Thank you. Does that answer your question?
Yeah.
Yes.
Okay, thank you.